Vielen Dank an Maximilian Beer und Jonathan
Thanks to
Großmann für
Maximilian
die
Beer and Jonathan
musikalische
Grossman
Eröffnung
for
des
this
heutigen
musical
Festaktes.
opening of today's
Sehr
award
geehrte Frau
ceremony.
Professor Schumann, sehr
Professor
geehrter Herr
Schuman,
Dittmar, sehr geehrter
Mr.
Herr Professor
Dittmann,
Kramer, sehr
Professor
geehrte
Kramer,
Abgeordnete,
members of the
sehr
Hamburg
geehrte Damen und Herren,
Parliament,
herzlich
ladies and
willkommen
gentlemen, welcome
zur Verleihung des
to
Körber-Preises
this
für die
award
europäische
ceremony
Wissenschaft
for the Körber
2024.
European Science Prize.
Auch wenn es in diesem Kreis bekannt
And
ist, möchte ich es noch einmal betonen. Der
even if it's
Körber-Preis
well known to
gehört
all
zu
of
den
you, I'd
bedeutendsten
like to mention it again. The
und
Körber
höchst
European Science
dotierten
Prize is
Forschungspreisen
among
weltweit.
the most renowned and highestly endowed science prizes in the world.
Er ist eine große Ehre für die Preisträger, aber auch
It's
für
a
die
huge honor
Wissenschaftsstadt
for
Hamburg
the award
und zugleich ein
winners,
starkes
but also
Statement der
for the
Körber-Stiftung
Scientific Hub
für
of
die
Hamburg
Bedeutung
and
von
the
Wissenschaft
Körber
und
Foundation.
internationaler
It
Zusammenarbeit.
underlines the
Die aktuellen
importance of
geopolitischen
international
Spannungen wirken sich
cooperation
auch auf die
and
Forschung
research.
aus,
And the ongoing
besonders
political
auf den
tensions have an
internationalen
impact also on
Austausch und
research,
auf
especially international
Kooperation
exchange and
angelegt ist.
cooperation is needed in
Hinzu
this
kommt, dass in
field.
vielen Ländern,
And
auch in
in addition to
Europa,
that, many countries also here in
populistische
Europe
Kräfte
we see
wissenschaftliche Erkenntnisse
populist forces
und die
which
Wissenschaftsfreiheit
deny
selbst
scientific results or
offen
the
oder
freedom
indirekt in
of
Frage stellen.
science. They question it.
Der Körber-Preis wirkt in dieser
And
Zeit
the
wie
Körber
eine
European Science
Gegenbewegung.
Prize is
Er betont die Bedeutung wissenschaftlicher
the wind
Evidenz
blowing in the different
und die
direction.
Freiheit
It
von Wissenschaft und
shows
Forschung.
that scientific evidence
Und er
and
wurde
freedom of science is
1985 mitten
important.
im
And
Kalten
in
Krieg
1985,
gestiftet,
right in the middle of
um
the
in
Cold
politisch
War, it
schwierigen
was
Zeiten
established so
Brücken
that
zu
in
bauen
politically
und die
difficult
wissenschaftliche
times
Zusammenarbeit auch über
we can have an
Systemgrenzen
impact,
hinweg
and so
zu
that
fördern.
scientific cooperation was to continue
Grenzüberschreitende
also different
Kooperationen
systems.
sind
So cross-border
eine
cooperation,
Stärke der
that is one
europäischen
of the strengths
Forschungslandschaft.
of the
Sie sind die
European
Voraussetzung dafür, dass
research
Europa
sphere,
im
and they are
globalen
prerequisite
wissenschaftlichen und
for
technologischen
making
Wettbewerb
Europe
bestehen
competitive
kann.
globally when it
Seit
comes
40
to
Jahren, wir
science and
feiern also
development.
ein
For 40 years
Jubiläum
now, it's
heute,
an anniversary year
setzt
this
sich der
year here. For
Körber-Preis
40
für eine
years, the
starke,
Körber
international
European Science Prize
ausgerichtete
here
Forschungslandschaft ein
has always worked
und
for a
wird
strong
dafür heute mehr denn
international
je
cooperation
gebraucht.
in science. We need this more
Sehr
than
geehrte
ever
Damen und Herren,
before
in der
today. Ladies and
Spitzenforschung
gentlemen,
sind die
in
Lebensläufe
excellent
international.
research we
Das gilt auch
see
für die
international
diesjährige
CVs, and this applies
Körber-Preisträgerin.
to this year's laureate
Erin
as well.
Schuman ist
Erin
in
Schuman
Kalifornien aufgewachsen,
grew up in
hat dort
California.
Psychologie
She
studiert
studied
und in
psychology
Princeton
there,
in
and
Neurowissenschaften
then
promoviert.
she received her
Nach
PhD
weiteren
from
wissenschaftlichen
Princeton in
Stationen in den
neurosciences.
USA
After different
wechselte sie
scientific stages in the
2009
US,
ans
in 2009
Max-Planck-Institut für
she
Hirnforschung
came to the
in Frankfurt am
Max-Planck
Main,
Institute
wo
for
sie als
Brain Research
Direktorin der
in Frankfurt am
Abteilung
Main, where
zur
she became
Erforschung
the
der
director of
synaptischen
the
Plastizität
Department to
leitet.
Research Synaptic
Erin
Plasticity.
Schuman beschäftigt
Erin
sich seit über
Schuman
30 Jahren mit
has
der
worked for
Frage,
more
was
than
beim
30
Lernen
years on the issue
oder Erinnern im
what
Gehirn
is
passiert.
happening when we
Ihr
learn
besonderes
or
Augenmerk gilt den
create
Synapsen der
memories.
Nervenzellen, also
And
den
the
Kontaktstrukturen
synapses, the contact
zwischen den
structures of nerve
Nervenzellen
centers in
und den
between these
Proteinen,
nerve
die
cells
für die
is what she's
Informationsübertragung
looking at.
nötig sind.
And
Sie
protein
untersucht, wie diese
synthesis
Proteine
necessary.
hergestellt
She
werden und
looks
an die
at how
entsprechenden
these
Synapsen
proteins are
gelangen
created
und
and how
stellte
they get
fest,
to
dass die
these synapses,
Proteine
and she
nicht irgendwo
found
in der
that
Zelle,
the
sondern
proteins are not created
an den
anywhere in the cell body,
Synapsen
but right
selbst
at
oder in
the
der Nähe der
synapses or
Synapsen
close to
synthetisiert
the
werden.
synapses. That's where the
Damit hat sie
synthesis
die
takes place.
lokale Proteinsynthese
And
als
so
einen
local
Kernmechanismus für die
protein
Kommunikation
synthesis is
zwischen den
therefore a core
Nervenzellen
mechanism
erkannt.
for communication
Das
between
Preisgeld
nerve
soll
cells.
Erin
That's
Schuman
what she
ermöglichen,
proved
ihre
here.
Forschung an den
And
Synapsen
the
fortzuführen und dazu
prize money will
beizutragen,
help her to
die
continue
Mechanismen des
research
menschlichen
and
Gehirns für die Erinnerung
to decipher
und das
the
Lernen aus
mechanisms
Erfahrung
in
weiter
the human
aufzuklären
brain. What happens
oder auch
during
neue
learning or
Therapien für
creating
neurologische
memories, or
Erkrankungen
how
zu
to
entwickeln.
create new therapies
Sehr
for
geehrte Frau Professor
neurological
Schumann,
disorders.
Ihre
Professor
wissenschaftliche
Schuman, your
Arbeit
scientific
über die
work
Proteinsynthese an
on
Synapsen
protein synthesis
wird auch
at
in Hamburg auf Interesse
synapses
stoßen.
is something that's also
Neuronale
very interesting in
Plastizität, Lernen und Gedächtnis sind
Neuroplasticity,
Schwerpunkte an
learning
unserem
and our
Universitätsklinikum,
memory, that's the focus of
an der
our
Universität Hamburg
university
und in einem
hospital at the
speziellen
University
Hub
of
für
Hamburg and in a
neurowissenschaftliche
special hub for
Forschung,
neuroscience
dem Hamburg
research
Center of
at the
Neuroscience.
Hamburg Center of Neuroscience.
Der Preis und das Preisgeld sind eine große Anerkennung Ihrer wissenschaftlichen Arbeit und Ihres Einsatzes für die Wissenschaft in Europa. Ich wünsche Ihnen im Namen des Senats weiterhin viel Erfolg für Ihre Forschung und auch persönlich alles Gute. Herzlichen Glückwunsch zur Verleihung des Körber-Preises für die europäische Wissenschaft 2024. Sehr geehrter Herr Erster Bürgermeister, lieber Herr Tschentscher,
Mayor,
sehr geehrte Frau
Mr. Tschentscher,
Frau Gümbel,
State Minister, Ms. Gümbel, Members of Parliament, Professor Erin Schuman, members of the Committee for the Körber European Science Prize, ladies and gentlemen, welcome to the awards ceremony of the Körber European Science Prize 2024. Ladies and gentlemen, we are not living in times which are characterized by optimism, hope and confidence. If you still watch the German news, the Tagesschau, every evening, you know what I mean, because it's just full of crises, and sometimes it's a little bit improved by the weather forecast with nice weather. However, during the climate crisis, this shouldn't be positive news either. Here at the Hamburg City Hall, the situation has been different for 40 years when we award the Körber European Science Prize, because we honor excellent achievements by scientists and their teams. And these are research, insights and innovations that promise a better future that never would have been expected by anyone. So the Körber European Science Prize is the last anchor of hope for solving the burning problems of the present and for a better life of the future. This is also reflected by its good reputation. Only medicine receives a higher level of trust than science. And this already explains part of the fascination for our prize winners, but it doesn't explain the long-term success of the Körber Prize. And I would like to celebrate this 40th anniversary this year and take a look back and ask for the formula of success. Why is this Körber Prize so special? And why isn't it even more important than 40 years ago? And where could we be heading in the future? Let's start with Körber's understanding of science. In science, the freedom of teaching and research prevails. It's the right thing to have this, but there are also obstacles, because it's disconnected from society. It's the ivory tower, which is one risk here. The other risk is that the potential of innovation and breakthroughs are not recognized if science is just focusing on its own questions and just focusing on its own discussions, because the big discoveries take place outside of the mainstream of research most of the time. For Körber, it was obvious that science cannot just get its legitimization from its own science. There was relevant and research which was not that relevant. So he considered science to be able to receive an award which promises to mark a significant contribution to sustaining the living conditions on our planet. That sounds almost absolute, because who actually knows in research what will become important? However, our perspective on science has also changed over the past 2 decades, because in difference to 1984, we are now very aware of the fact that our living conditions are at risk on our planet, and we know that research and science have to make a contribution to sustaining the living conditions. There was never a question with the Körber European Science Prize that people focused on the living conditions. It was against the fight against AIDS in '86 and malaria in 2007, vaccines and genetic optimization of arable crops in 2001, and we also focused on new storage technologies for batteries in the year 2021. And it has always been the target, the objective, to make a step ahead and not just follow a trend. Just one example, in the year 1990, the Körber Prize was awarded to 3 scientists, amongst whom were Klaus Hasselmann from Hamburg. They were the pioneers in the field of climate change. Back then, people really didn't focus on that topic. And in 2021, they received the Nobel Prize. Prize for their work. So for 30 years, the Körber European Science Prize focuses on the social added value and the future potential of science. So we already get a glimpse inside the labs and what's going on there. We can participate in the adventure of developments, and every Körber Prize is also a promise for a better future.
This focus
on the added value and the potential of research also has an entrepreneurial aspect. And this gets even clearer if we focus on the scientists and researchers. As soon as Körber was convinced that this was the right thing, he also managed risks or accepted risks. At the end of the day, this led to a prize where we don't have any applications, where we don't need any reports or proofs of feasibility, because Körber knew that for entrepreneurial activities you have to be flexible in order to be successful. And Körber wanted to promote this entrepreneurial mindset. And this is also a message to the politicians. Research and science also face obstacles due to bureaucracy and red tape. And honestly, this hasn't changed over the past few years.
Körber war davon überzeugt, dass es vor allem darum geht,
Kurt
die
Körber
richtigen
was
Menschen an der richtigen Stelle in die
promote the
Verantwortung zu
right
bringen
people
und
at
ihnen
the
dann
right
eine
place
optimale Umgebung der
to
Entfaltung
take them
zu gewähren.
to accountability
Ist das
and to
klug
give them a
oder
right
naiv?
level of
Für
responsibility.
uns hat es sich
Is this smart
jedenfalls
or
mehr als
naive?
bezahlt
For
gemacht.
us, it really paid
Hochgradig
off,
intrinsisch motivierte Menschen
because
arbeiten
these are
bekanntermaßen
intrinsically
besser
motivated
und erfolgreicher als
people.
solche, die engmaschig
And
kontrolliert werden.
They are
Und dazu gibt uns die
much more
faktische
successful than
Bilanz
those
recht,
people who are really
denn jenseits
controlled
ihrer
and
Forschung haben
managed
fast alle unserer
closely.
Preisträgerinnen und Preisträger
And this
aus
is
den
true
letzten
for the
Jahren
success of
Firmen
all the
gegründet,
prize winners from the past few years.
Anwendungspotenzial
They
ihrer
founded
Arbeit
companies
zur
in
Geltung
order
zu bringen
to also
und
apply their
unternehmerisch
research
tätig zu werden.
and to
Und
become
ein letztes
entrepreneurial.
Faktum,
And I
so
have
ganz
one
falsch können wir
last
nicht liegen,
fact for you.
wenn allein in den
We
letzten
cannot be
15
too
Jahren
wrong, because over
7
the past
unserer ehemaligen
15 years,
Preisträgerinnen und
7 out of the
Preisträger
former
auch
prize
den
winners
Nobelpreis
have also
erhalten
received the
haben.
Nobel Prize.
Der Nobelpreis, und das sage ich wirklich ohne Wertung, liegt allerdings hinter der Welle. Er ist immer die Anerkennung für ein Lebenswerk. Das ist absolut berechtigt und wichtig. Es hätte aber eben nicht Körbers Mentalität entsprochen. Schließlich zu einem dritten Aspekt, der den Körber-Preis besonders macht und der eben auch vom Bürgermeister schon kurz erwähnt wurde, die europäische Dimension. Es gibt tatsächlich, und darüber wundern wir uns manchmal selber, keinen weiteren renommierten Wissenschaftspreis, der in ähnlicher Form Europa in den Fokus rückt. Denn für den Körber-Preis kommen ja nur Wissenschaftlerinnen und Wissenschaftler in Frage, die in Europa forschen und leben. Wir freuen uns unter Marketing-Gesichtspunkten über diesen USP, aber wir stellen auch immer wieder fest, dass es noch immer keinen europäischen Resonanzraum gibt. Berichtet wird vor allen Dingen
national. Und
No
selbst in den
European
Ländern, aus
feedback
denen unsere
area.
Preisträgerinnen und Preisträger kommen, bleibt es meistens eine Randnotiz.
Most of the
Da
time,
ist noch
the
Luft
news
nach
only
oben.
report about it nationally, and
Körber war
there's
ein
actually
Zeitgenosse
room
von
for
großen Europäern
improvement.
wie François Mitterrand und Helmut Kohl, den
Körber
ich auch dazu
was
zähle.
inspired by François
Für ihn war die
Mitterrand and
Wissenschaft einer der
Helmut
Bereiche, in dem
Kohl.
es
For
dringend mehr
him,
an Europa
he
braucht.
said
In nationalen
that
Alleingängen
science
werden
and
die Europäer
research
nicht mehr
needed
viel
more of
erreichen,
Europe.
lautete seiner
We
Überzeugung
cannot
schon Mitte
achieve
der
more if we only
1980er
focus
Jahre.
on national
Tatsächlich, auch
borders.
das
This
wurde
was
eben schon
already his
angesprochen,
credo in the
ist die
80s.
Wissenschaft ja
And
wie
it's
kaum
true,
ein anderer gesellschaftlicher Teilbereich
For him,
internationalisiert.
science and research is
im
international,
Sinne
and
der
it's true,
ursprünglichen
it
Herkunft
is
spielen beim
internationalized.
Körberpreis schon lange keine Rolle mehr.
So
Die Teams
origin
sind
doesn't really play a
heutigen
role with the
Vokabular
Körber Prize.
divers
The teams
zusammengesetzt.
are
Entscheidend
diverse,
sind allein Kompetenz und
and what's
Spirit.
decisive is
Gleiches
competence and
gilt für
spirit. The
Wissenschaftsräume, wie
same
etwa den
holds
in
true
Hamburg.
for science
Forschungseinrichtungen wie das
forums,
DESI
such
oder das
as
Bernhard-Loch
here in Hamburg.
Institut
We have
leben
the
von der
Bernhard-Loch Institute
Internationalität.
and DESI
Hochschulen
here
wie
in
die
Hamburg,
Universität oder die
and
HAW
we
Hamburg
have the
holen
HAW
Studierende aus
Hamburg,
der
the
ganzen
Universities
Welt.
of Applied
Englisch ist
Sciences,
längst die
and they
Lingua
want to
franca
attract
dieser Community.
talents from abroad. English is the lingua franca here. What's also interesting is to focus on the political tensions in our society, because this level of internationality is never questioned from no political parties. People know that excellence, expertise and competencies cannot be limited by nationalities, and this diversity is a huge asset for Germany and Europe.
Für den europäischen Forschungsraum, und da wende ich mich der Zukunft
For
zu,
the European Science Area, and this is where I look into the future, we want to promote the Körber European Science Prize even further, and we are very delighted that Hamburg is supporting us in this endeavor. Together with the Ministry and authorities of education, we have created the European Science Forum. This is connected to this awards ceremony, where politicians, society and civil society come together under the motto "Crossing Borders, Building Bridges." We are focusing on the current challenges of European science and research. Yesterday, the first conference took place. It focused on new technologies, and I just want to mention one aspect of the keynote of the former Minister President of Italy, Enrico Letta. He says that the European internal market is so important. We need the free flow of people and material, and we also need free circulation of research and education. We believe that this could lead into a new phase of European cooperation, because at the end of the day, we have to ask ourselves, where do we Europeans get the confidence to compete globally and to assert ourselves? Democracy is often mentioned here as the common value, as the basis for that. However, the second European invention is also important. Modern science is based on the fact that we have to use good and measurable arguments. Rationality, this is what we're talking about. In addition to democracy, rationality is the second and indispensable pillar of our European identity.
Am Ende, und damit schließt sich der Kreis,
at the
werden
end
solche
of the day,
Grundsätze allerdings nur glaubwürdig durch
principles,
die
however,
Menschen,
only become
die sie
credible
vertreten und
through
leben.
people.
Erin
They
Schuman
represent
ist
these
geradezu das
values. And
Musterbeispiel
Erin Schuman
für dieses
is a role model and a
europäische
pioneer
Selbstverständnis.
for this
Sie hat durch
European
Exzellenz, Kreativität und
mindset. Through
Hartnäckigkeit
excellence,
ein
creativeness
Rätsel
and
gelöst, auf
persistence,
das sich die
she
Hirnforschung
solved
bislang
a
einfach keinen
problem
Reim machen
and a
konnte.
miracle
Das Rätsel
for
der
brain research,
Proteinproduktion
the
in den Neuronen.
a question of
Im Kern
protein
handelt es sich
synthesis
dabei,
in
das haben Sie eben
neurons.
schon
You
gehört,
already
um ein
heard about it.
logistisches
It is
Rätsel.
a
Wie um Himmels
logistics
Willen werden die
question.
Hunderttausende von
How
Proteinen,
can the
die an den Synapsen von der
100,000s of proteins
Informationsspeicherung
which are
über die
needed at the
Signalübertragung
synapses for
bis zum
information
Aufbau von
storage
Hirnstrukturen
and
gebraucht
making
werden, und
memories
zwar
and
genau
building
in der richtigen
inhibitors,
Menge, genau
be
zur
provided
richtigen
at the
Zeit?
right
Wie
point in
werden diese
time,
Proteine
at the
über
right
die großen
volume?
Entfernungen
And how
von
can
den
these
Zellkernen bis
proteins
zu
be
den
transported from
vergleichsweise weit
the
entfernten
nuclei
Synapsen transportiert?
to the
Dafür hatte
synapses which
niemand
are
eine
far
Lösung,
away?
bis
And nobody came up
Erin
with a
Schuman
solution
die gängige
until
Sicht auf den Kopf
Erin
gestellt hat.
Schuman turned
Schumans
things around.
schlichter und zugleich revolutionärer Gedanke,
Schumann's
das
simple and
Logistikproblem
revolutionary
existiert
idea
so gar
said
nicht,
that
denn die Proteine
this
werden
problem
überwiegend nicht
doesn't
im
really
Zellkern
exist because the
produziert,
proteins are
sondern
not being
dezentral
produced
dort, wo
in
sie
the cell
gebraucht
body, but
werden,
decentrally,
nämlich an
where
den
they are
Synapsen
needed at
selbst.
the
Das
synapses.
hört sich simpel an,
It sounds
hat aber
simple,
fundamentale
however,
Konsequenzen,
this has
denn nun
a
ist der Weg
fundamental
offen für ein
impact
neues
because now
neuronales Verständnis
we have a
und
new
zugleich für
understanding
neue
of
Therapieansätze.
neural networks, and now we can look for
Erin
new
Schuman ist aber im
therapies.
besten Körberschen Sinne nicht nur
In
eine
the
brillante
sense of Kurt A.
Preisträgerin,
Körber,
sondern
Erin
auch
Schuman
eine
is a
wache
brilliant
Demokratin
prize winner.
und eine
She is
engagierte
also a
Mentorin
Democrat
für den
and she is
wissenschaftlichen
also
Nachwuchs.
a mentor
Sie
for
unterstützt
scientific
insbesondere
new
junge
talent.
Frauen,
She is supporting young women in their careers in technical and science-related subjects. And together with her husband, she is committed to also making the crimes of the Kaiser Wilhelm Institute visible of the Second World War. You have to know that the Kaiser Wilhelm Institute is the predecessor institute of the Max Planck Institute, where Erin Schuman is working today. Ms. Schuman, we admire you for your scientific work, and we also respect your democratic commitment. Congratulations on the Körber European Science Prize 2024 on behalf of the Foundation and the committees. As always, I would also like to thank our search committee and the trustee committee, because they made sure that we have this high-level prize winner. And I would like to thank our mayor and Ms. Gümbel, our state council member. Thank you so much for hosting this award ceremony. Thank you very much for your hospitality in this great ballroom. I can only highlight once again that this event in the living room of our city shows the appreciation of the Körber European Science Prize and the importance of science in Hamburg. You all came here in order to get excited about what science and research can achieve. So with that, I would like to pass the floor to our host, Helen Czerski. Together with our laureate, she will give us insights into the inner life of our brain cells. Thank you so much.
Hello, everyone, and isn't it wonderful to be back in this fabulous hall to celebrate another Körber Prize winner? I would also like to welcome the guests on the live stream, so it's not just us in the room. This prize is known now by more and more people, and so hello to all the people watching around the world online. And the thing that's exciting about being here every year is that it's a real moment of celebration. We know that science is about advances, and that these advances change how we think the world works or how it could work. And the fantastic thing about science is that this is an adventure. There is always more to explore. So of course, there are practical outcomes, very important practical outcomes to the science. But there is also the joy of curiosity. And the wonderful thing about being human is that we can keep exploring. And the Körber Prize is a wonderful celebration of that exploration. So the event from now on will mostly be in English. So there are headsets. Maybe some of you saw them on the way in. And the headsets will make the translation available via headphones. And the other thing, just before we get started, of course, one of the applications of the work we'll be talking about today is memory. And so I would like you to think, as you're going through the ceremony, about the memories you're making today. Have a think about what's going on in your brain as that happens. And of course, we'll be talking about that in a couple of moments. So you've already heard a little bit about the prize winner, but now we will have a video that was made by Wagner Visions, and this introduces Erin Schuman and her research at the Max Planck Institute for Brain Research in Germany. Here's the video. Erin Schuman, director at the Max Planck Institute for Brain Research in Frankfurt. Her work focuses on a particular kind of cell, the neuron. Billions of these versatile nerve cells manage all of our senses and, among other things, enable us to watch this film.
Neurons are probably the most interesting cell you can find in the body. They underlie everything that the brain does. So everything we do as humans, as animals, perceiving the environment, reflecting on the environment, and reacting to the environment, this is all done by our brain. And neurons are the principal cells in the brain. What makes them particularly interesting is that their shape is suited to interconnecting with each other. That's what's so fascinating about them.
Every neuron is equipped with long extensions, dendrites and axons, for receiving and sending stimuli. Essential for this kind of communication are the synapses. Erin Schuman and her team were able to show that the synapse is where many proteins are formed, which are essential for those nerve cells to function properly. Neurons were long thought to produce their proteins centrally in the cell body. That nerve cells are capable of producing proteins locally at the synapses, that is new ground, broken by Erin Schuman and a milestone in brain research. In addition to such discoveries, the team are also pioneering methodologies in the lab. They grow nerve cells in special microfluidic chambers. This allows the researchers to study the nerve processes independently of the cell body. Thanks to these small chambers, the role of proteins can now be visualized outside a brain. Special dyes make the microscopic components of our perception visible. Here in green, nerve processes of neurons grown in the lab. This clever method makes deeper insights possible.
If we look in the brain, we of course see a mix of cell bodies and dendrites and axons. And in these microfluidic chambers, what we're able to do is force the neuron to send its axons and dendrites in a linear array so that they're lined up perfect for us to visualize exactly what's going on in the dendrites and the axons.
Ingenious inventions like the microfluidics chamber improve basic research on nerve cell function, but they also help investigate diseases in which synapses play a big role. The connection from one neuron to another is particularly sensitive and susceptible to damage. Genetic defects can cause synapses to malfunction.
There's a surprising amount of convergence that many of these diseases appear to have synaptic dysfunctions that are apparent. So synapses aren't working well in the brain.
There could be too many synapses, too few, or the production of the all-important proteins is disrupted.
And this is exactly what we study. So we think that the methods we have developed, if we look at disease models, can give us a very clear picture of what's wrong with these synapses in disease states.
Mice are used as model organisms, substituting for humans. Sick and healthy individuals are compared to find out what causes certain diseases. This is the very first step towards developing potential treatments. The brains of mice with genetic defects, such as Fragile X syndrome or Huntington's chorea, show significant differences. Erin Schuman and her team want to understand how the synapses are affected. Apparently, the protein synthesis of neurons differs depending on where they're located in the brain. This calls for even more high-tech methodology.
It's very important to be able to resolve and identify the synaptic proteins at a particular cell type. And that's a method that we've developed in the lab now, where we can purify synapses from a certain cell type in a certain brain area, and therefore have a very refined view of what could be going on in these disease states.
Being able to look inside a mouse's brain, visualizing neurons and analyzing proteins may one day lead to help for patients who suffer from synaptic dysfunction inside their brains. In order to reach this far-off goal, the mice's brains are dissected and the proteins within carefully analysed. Using their highly specialised lab techniques, the team are able to isolate proteins of specific kinds of synapses for further study. These proteins appear to be basic elements of our perception, involved in learning and in the storage of memories. But these structures are very short-lived, which raises important questions for the researchers.
The average protein that we study, half of its lifetime is over within 5 days, and yet we know memories can last a lifetime. So the question that really drives us is, how can we understand a system that gives rise to something stable but is built from unstable parts, the proteins?
The team at the Max Planck Institute have found an ingenious way to study the ephemeral proteins. They don't only look at the proteins, but also at the mRNA, which is the molecular blueprint for any given protein. Schuman's team have come up with dozens of innovative ways to study the brain. Their methods have already led to new insights that may one day be of great use to patients.
Right now, we're on the cusp technologically of being able to see things in cells in ways that we never have been in the past, being able to visualize them near synapses, and I think the next 5-10 years are going to be super exciting and really illuminating for us to understand how these processes work.
Erin Schuman is paving the way to the fascinating world of neurobiology and a better understanding of how our nerve cells function. And of course, the video is wonderful, but isn't it better to hear from the person themselves? Erin Schuman, please come to the stage. Okay. Now, there is so much to dig into here, but I wanted to start with a sort of abstract idea, because this is all about memory. And I just wondered if you could tell us of a memory you have from perhaps a long time ago that we can use as an example.
I guess something relevant to our discussion today. We moved to Germany in 2009. And a memory I have from 2008 is when Gilles and I decided we needed to tell our daughters we were moving to Germany. And we met at the breakfast table in Pasadena, California. And we told the girls, who were then 5, 9, and 13, we have some news. We're moving to Germany. And there was a little shock and sort of nodding, and then, well, why? Well, Dad and I are setting up a new brain research institute in Frankfurt. And they said, okay. And then Charlotte, who was 9, said, but wait, why are we moving? And we said, well, we're moving to do our science there. And she said, well, people don't move. And Gilles said, yes, people move. We move to different places. And she said, people move to Seattle. They don't move to Germany. And so, the end of that story is, of course, that the girls really enjoyed the move, and if you asked them if they would do it again wholeheartedly, they would. It's been fabulous for them. But we all laugh about this family memory.
Who would move to Germany? But the lovely thing about this, of course, is that memory is a critical part of being human, and you've just demonstrated it beautifully. We identify ourselves in terms of our memories and those stories, those moments in life, which are really important to us. And the mystery, of course, the scientific mystery, is that it's all in here somewhere. That in the physical nature of a human brain, somewhere there is an idea that you were sitting at a kitchen table and explaining something to a child, and that is an astonishing thing. Just talk to us a bit about that. This incredible idea that little molecules in here can somehow conjure up your kitchen table.
Right, so, I mean, when you think about memory, there's so many components to it, so many sensory systems. You know, your vision, the memory of the conversation, maybe even the memory of the smells of the breakfast table. So all those things come in via their relative sensory channels, the eyes, the nose, the ear. They come into the brain, and of course, the information is coordinated and integrated at the connections that we saw in the video, the synaptic connections. And our current thinking is that the information is stored by altering the strength of the connections between those relevant areas. So the sensory pathways that converge in a certain integrative area, those synapses there are altered, and they're altered for long term. I mean, this is, I think, still the big mystery, and the thing that keeps us going is how you actually get. It's easy to think how to set something up, but how do you get it to persist when the molecules themselves, the proteins, as we heard in the video, are rather short-lived. They live for days, not for years.
Well, there's plenty of science still to do. So let's just spend a while on how you got to the stage of moving to Germany to do brain science, because you didn't start out in neuroscience, and you went through, there's this wonderful transition in your career where you went from working with human twins, identical twins, to sea slugs, which is quite, those are two quite different experiences. Just tell us how you go from the twins to the sea slugs.
So, as an undergraduate, I was doing my honors thesis on these twins. I was studying learning, so I was already at that time very fascinated in how the brain is storing information. And as you may know from twin studies, you can infer how much genes and how much environment contribute to cognitive abilities. And so I came to the conclusion that 50% of memory ability is genetic and 50% is from the environment. But the process of doing science, at least for me as an undergrad with humans, was chaotic. I was driving my VW Bug to people's houses to test their twins, and there were too many uncontrolled variables for my liking. And so I think that that's the reason I migrated to a system that arguably at the time was one of the only systems where you could really study learning and get resolution on what the brain was doing, was in these invertebrate species, which show magnificent learning. So the animal that I studied shows Pavlovian conditioning. So it learns to associate a stimulus with a natural stimulus, and you can change the animal's behavior. And I was able to poke electrodes into brain cells and, really study memory, what had changed in the brain as a result of this behavioral experience.
Amazing. And of course, this is the way science goes, that these paths aren't always obvious. And I love that about it, that there's so many things to study. Let's cover a little bit of the basic science, because I think that one thing that we've almost got used to when we talk about biology is cell theory. This idea that the basic unit of life is a cell. And we see that as a small thing. I can't remember the number, but we are made up of billions or trillions of cells. And so we think of a cell as a small thing, but then actually every single cell is a little factory. So just tell us a little bit about a normal cell before we get to the neurons, and this amazing little factory that each little cell is.
Right, so within the cell, as you say, we think of the cell as unitary, but it is full of small little compartments that are doing their own job, right? Little factories that are making proteins, making energy, degrading proteins, getting rid of contaminants. And the thing about the cell as we see it is that it's hard to visualize those little areas within the cell. So the neuron, in some ways, can be viewed as an opportunity to understand the function of the cell, because it has done us the favor of moving those subcellular compartments and factories out and separated them from the cell body so that we can see them better.
So that's what we saw. So a normal cell is more or less a lump, but then the thing that's different about the neurons is they've got these extraordinarily long things that come away from them. And just tell us a little bit about so the thing that's at the end of all these long tendrils, those are the synapses, the connections. And so tell us a little bit about how, clarify, I mean, we heard a little bit in the video about where the proteins were generated, but why was it a big deal that the proteins were generated in these long fingers rather than in the cell body?
Right, so our understanding of how the neuron as a cell worked was based on decades and decades of beautiful work done on these round cells. And so the assumption was, when people first looked at the neuron, was, oh, well, I see the round cell. All of that other stuff is where the synapses are, but I see the round cell, and so I just need to copy-paste my thinking of how that round cell worked right onto the neuronal cell body. And it just was never questioned that all of the machines in the cell body were still in the cell body, and those machines had the heroic task of actually sending all of their products, the energy, the proteins, all of that out into those processes, which I don't know if your eye could allow you to assess the relative volume, but the axons and the dendrites, the processes, are the majority of the volume of the cell. So historically, we were asking a relatively small little ball to supply all the goods that are needed for this massive volume. So in retrospect, it makes sense what we've discovered, but at the time, the thinking had just transferred the cell body from other cells to neurons, and so that was the dominant assumption.
And let's just talk a little bit about how you got there, because of course, to see the insides of a cell functioning is very difficult because you can't just open it up. You might be able to put an electrode into a sea slug, but you can't do that with a cell, because if you burst it, it stops functioning. So how do you see inside the cell to see how things are happening?
Right. So, I think, like many things in science, we got into this very indirectly. So we were doing experiments, actually recording synapses with an electrode, but very far away from the cell body. So we were way out where the synapses were, and we were studying how synapses change. And we had made the synapses stronger with a drug. And there was a lot of discussion, actually dating back from the 1950s, and people had been ruminating on what is the physical substrate of memory. And there was already knowledge that, actually from whole animal experiments, that in order for animals to show memory, the brains of those animals needed new protein. And this was done by injecting inhibitors of protein synthesis into animals during learning.
So just to clarify, if you can't make new proteins, you can't form memory?
Long-term memory.
In the long term.
Yes,
yep.
You cannot form a long-term memory. So we did the sort of in vitro version of that experiment, and we put on a drug that blocks the synthesis of new protein. Now, if the protein is coming from the cell body, you would imagine that when you change the strength of the synapse, that you would have to wait some time for those new proteins to come and be delivered. But instead, we had a very surprising finding that there was an immediate effect of applying that drug on the learning we were looking at. So it told us it was within minutes that we could see a difference when protein synthesis was blocked. So then we went on to do experiments to really physically isolate these synapses and show that the protein synthesis was coming from that local source. But what's interesting in what you suggested, actually, is that this was a very indirect method, right? We have an electrode in a piece of brain, and we have a drug. And I'm trying to convince myself and everybody else that inside these synapses, there are machines and there are messenger RNAs that are making proteins. So that's the rest of the story, really, is doing those kind of experiments.
It struck me when I was thinking about this that it's a bit like supplying the International Space Station, that, people always had to put things on a rocket and everything had to be carried and everything has to be carried there, and it takes a long time. And of course, now people are thinking about 3D printing spare parts on the space station. And it's sort of a similar, it's much quicker, it's obvious, it's much more efficient. But when you first suggested this idea, it's always difficult when you sort of suggest a new idea in science. What was the reaction when you first said, well, maybe the things we had been thinking, maybe we weren't getting that right?
The reactions were very strong and very discouraging. They went from, that's crazy, I was junior at the time, right? So some senior people tried to gently guide me away. You're not really going to work on that. And then I really decided I really want to study this. And I remember people sort of, raising their eyebrows like, oh, you're going to really invest in that. You're going to go for that. But I hope that maybe I've conveyed how interesting this is as a problem. And I really felt captivated by it as a logistics problem and as a problem of how cells work. And I guess that we weren't deterred by that. In fact, maybe I was in a weird way kind of decided to prove everybody wrong.
There's an element of stubbornness in that, which
definitely.
is very, it's not always a bad thing.
Yes.
And so once you had the idea that this is what's happening, was it obvious what to do next? What kinds of studies to do to take the science forward?
It was also, I should say that, this work was not done in a vacuum. So I think part of the inspiration that we were on the right track came from some contemporary discoveries. So Kelsey Martin working in Eric Kandel's lab and Christine Holt working in a developmental system, both had similar discoveries. So in that sense, I also knew I wasn't crazy, but it was very clear. I would say the roadmap was very clear. It was really terra incognita. We knew very little about what the components were out in the dendrites and axons because, of course, everything had been focused on the cell body. And when I say components, when you think about making a protein, you need the template, the messenger RNA, which hopefully we all know about after COVID, saved us, the messenger RNA. You need the machines. So you need the machines, the ribosomes, which are going to read the messenger RNA. And these were huge things that we needed to look into because at the time, the number, let's say the diversity of what could be made, so individual neurons express 7,000 different proteins, and only 10 messenger RNAs or so had been seen in the dendrites. So this said, if this is an important process, are these 10 messenger RNAs actually going to change the synapse? So that meant we had to discover the messenger RNAs and see what that population was to discover the potential for what could be made at the synapse.
So the messenger RNAs are kind of carrying the recipe.
Correct.
And then you have all the material. Presumably you need transport networks that are taking the raw materials.
Yes,
so you up and down.
You have to transport everything, right? So things can diffuse in cells, but most of what gets out to the dendrites and axons travels on these superhighways with motors that actually drive them. So that is required. But the thing that's interesting also in terms of a numbers game is that a messenger RNA can give rise to many copies of proteins. So you get a lot more bang for your buck by transporting the messenger RNA because you can make 100 or more copies of a protein, whereas if you had to transport 100 proteins, that would cost a lot more.
It never ceases to amaze me how all of this intricate machinery, you're talking about individual molecules moving around, these little ratchets that are moving things around the cell, and somehow we can see into that without being able to see it. It's really impressive detective work. Do you feel like a detective?
There are certainly aspects where we do feel, and then there are moments when you actually see things. So I would say that we're at the cusp of actually increasingly being able to really see these things. So the motors that you're describing, we can see now. So we can see the machines moving along the highways and transporting things. And I'm sure everybody who does this kind of work feels the same way, like how amazing it is to actually see the thing that you've been studying and sort of inferring, and all the pieces of evidence line up and tell you that it's got to be there. And then when you actually see it, it's really amazing.
And humans, we do say in English, at least, seeing is believing.
Yes, yes.
You're definitely sure you're right.
Yes.
Well, just let's talk about the significance, because of course it's very interesting. You know, there's lots of humans like solving puzzles. We like to understand things. So it's interesting for its own sake. But once you know this, what happens next? What can we do with that knowledge? Or how does it change how we think about, you know, memory formation in humans? Why is it important?
So there's two things. One is I'm a champion of, I find just understanding incredibly gratifying, and I think it's something that it's a luxury to have as a human, that we can understand the universe and that we can understand how things work. I think we, like other animals, are naturally curious and we want to understand relationships between things. So that's one aspect. And then there's the more also human and practical aspect, which is that, as mentioned in the video, I think over the last 10 to 15 years, there's been a surprising convergence in many fields of pathology, neurodevelopmental disorders like autism spectrum disorders, neuropsychiatric disorders like schizophrenia, and also neurodegenerative disorders, that, of course, we know that these are brain diseases and therefore something is wrong with the brain. And we've measured the electrical activity and we know that the communication has broken down. But there's been really a focus and an appreciation that many of these disorders converge on the synapse. So they're not just, you know, general communication disorders. Many of the proteins, actually, that are the risk factors for autism spectrum disorders, for example, are actually proteins that are present at synapses. And many of interest to us is many of those proteins actually have their messenger RNA and are mostly made locally. So after years of doing this very basic research, we see ourselves now very close to important human clinical questions. And I think we're in a position where we could really understand the core problems at many of these disorders, because we're in a position now where we have the synapse in focus and we're able to see the mRNAs and the proteins that are there. And then, of course, once you can see the synapse and potentially control the components, you have potential avenues for correcting things with therapies.
So we should be clear that, you know, any potential therapies are coming from this idea are a long way off. You know, this is very basic and it's really important, but it's almost just, this is just the first step.
Correct. So in fact, I mean, I think it's very important that we all do what we're good at, right? So throughout the course of my career, every time we make a discovery, there are either students or postdocs or collaborators from the outside who want to come and want me to study a particular disease. And I have felt that my energies are best spent at what we do really well. And that is to study these very basic processes and develop new tools to look at them with better resolution. But so for the first time, actually, I feel that we've got enough information and the tools are so good, and we do have models available. So for the very first time, we are now setting up to do experiments where we will look at a few disease models. So these are mice where a model is developed for a specific disorder. So if a disorder, like one of the ones we're going to look at is Fragile X syndrome, which is a single protein that is essentially deleted. And this is a particularly interesting example because this protein is present at synapses and it actually regulates whether proteins will be synthesized or not. So there's a mouse model that we can look at that has the same genetics as humans, but also has some of the same symptoms as humans. And we will be able to look at these synapses in detail and see what's different about these synapses. We can do the same thing for other diseases too.
Brilliant. Well, what's great about this is you don't sound like you've finished.
Nope.
Well, just on the broader question, I'm interested in, you know, the Körber Science Prize obviously recognises European science. And I was wondering how you found working in Europe versus working in the USA. Obviously, they have different strengths and weaknesses. And I was wondering how you found that transition.
Yeah, so I mean, I think I've now spent about half of my time as a team leader in the US and in Germany. And one of the things that I've really appreciated about working in Germany is actually probably represented by all the people in this room, that it's in the culture and in the education of people in Germany, and I hope I could say in Europe, that science is important, that we can understand the universe, that facts are important, that there's a logic and a reason, and if we research things, we can understand how life works. So there's a respect that I've felt working here, also as evidenced by the enormous contributions of taxpayers to what we do, that is sadly, I would say, being challenged in the US. And that's, I would say, a really big difference between the two places.
Great. Okay, let's talk a little bit about the future. As we said, you've not finished yet, but also about the structure of science, because I think before we get to what you'll do with the prize money, I know it's very important to you that science is representative, that we know that the science that is done is not objective, right? It does depend on the people who are doing it and on their incentives. And you have put a lot of work into encouraging groups who perhaps haven't traditionally been part of the scientific world to come into science. Could you just talk about why that's so important to you?
Well, I think it's part of maybe what has been articulated recently when we think about diversity. But if you think about the hard problems we have to solve, there are many solutions and there are many approaches, and we all think differently. So I think the more minds we have to approach a problem, the better. So, and given that the way we think is influenced by our genes, but also by our culture and our upbringing, I think the more cultures that we bring to the table to think about how to approach these things, the better. And the more, that includes men and women. So that's my philosophy, more or less, that it really is about solving the problem. There's also the issue of fairness, but I think one need not invoke that, because it's really, if your goal is to solve the problem, you need the best minds with the most different perspectives to come in to think about how to do it.
And of course it takes, yes, that's and of course, these are complex problems, and that involves a team. And I know that some of your team are here in the audience today, and that you're proud of your team. You recognise they're part of this as well.
Yeah, I mean, so I'm sitting here as the winner of this prize, but I have worked with incredibly talented students and postdocs, and also amazing staff. I mean, the people that I invited here today are the technical assistants and my assistant. They are absolute masters of their craft. They are the reason that we can do things like grow those neurons in those chambers. They are incredibly skilled. They have a discovery mindset, and they're really part of our success. And one of the things that I feel so privileged, being a scientist, is how lucky we are to actually do this job, to be able to discover things. It's a real luxury, I would say, as a human. And I think we need to make sure that everybody who's involved in this enterprise feels part of that success, because they're so essential for the success. And so this is something that we've tried to do in our own institute, which is to first show our appreciation, but also let everybody have a little bit of ownership of what we do, because of course these are really hard problems, many very difficult methods, many widgets to make in the machine shop, IT needed, temperature control, all of that. But it's, if you just look at that, you think, oh, you're controlling the temperature of the room and the humidity. But actually, no, if you don't do that right, everything collapses. So it's really, the whole enterprise is so important. And, I feel a great deal of appreciation for the people who I have with me now, and a lot of respect. But also, I would say, over, the decades that I've been doing this.
Brilliant. So I think that's really important, partly because it changes the stories we tell about science, because the stories that perhaps you and I were told at school were that, there was a lone scientist and they worked in their lab and then 20 years later they emerged with a solution to some massive problem. And of course it wasn't really true then, and it's certainly not true now. And I think we need to change these stories. So stories like yours are really important. Now, of course, the Körber Prize comes along with a great big chunk of money, and you get to do lots of interesting things with that. So tell us a little bit about what your plans are for the prize money.
So I mentioned this just a few minutes ago. So what we've decided to do is to take a pipeline that we've been working on. So if you think about brain synapses in general, you think about the brain packed with probably 100 trillion synapses. Those synapses are not all the same. So different brain areas have to have different properties because they carry out different computations. And we know about how those brain areas function in terms of their electrophysiology, but we don't actually know about the synapses, which are really the business end of the thing. So we've developed methods that allow us to isolate certain types of synapses from certain cell types and look at them in isolation. So if you think about it, instead of taking the whole brain and getting all of the synapses where you might have, black synapses and white synapses, and when you mix them all together, you just see gray. So you would just conclude, and actually there's really no gray, right? There's no gray synapse. There's a black synapse and a white synapse. So it can be incredibly misleading to average, basically. So the beauty of the pipeline we've developed now is that we have this resolution to get synapses from certain cell types. And with that resolution, we're now going to look at these disease models. So we're going to be able to really say it's this cell type in this brain area and that set of synapses that is particularly affected. And along with that comes, of course, if one were to imagine clinicians thinking of a therapy, that resolution is very important because many of the inroads we have for therapy need to be more specific. You don't want to treat an entire brain when a very small nucleus in the midbrain is really what the problem is. So this kind of specificity and targeting will be really important for therapeutics, I think, as well.
Brilliant. It sounds like there's loads of exciting things to come. So just to finish then, I mean, scientists are good at generating questions. You can be good at answering a question, but you have to ask it first. And I was just wondering, looking ahead, is there one big question that you'd love to get an answer to? It's always hard because there's always too many questions. But is there, if someone said, you can choose, and in 10 or 20 years, we're going to guarantee you can answer this question. What's your question?
Wow, that would be a gift. For me, right now, I've spent, the last few years thinking and talking about these ideas, and the one thing that I think we're just about poised to do is to look at the persistence of memory at synapses by following the proteins. So we can take snapshots now, but I would like to actually look at a memory over time and see how it manages to persist in the face of this ongoing turnover of proteins at synapses. And I think we have the tools now where we may be able to do that. That's a dream experiment for me, maybe a bit nerdy, but...
This is the Science Prize. We are allowed to have nerdy dreams. Erin, it's been such a pleasure to talk to you. Thank you so much.
Thank you.
Great.
Sit down.
Brilliant. So now I would like to invite Professor Patrick Kramer, who is the chair of the Körber Prize Trustee Committee, to come to stage to have a short discussion about this prize and some wider issues. Please welcome Professor Patrick Kramer. So you are the chair of the Trustee Prize Committee. You were actively involved in the selection process. Just tell us a little bit about what makes Erin Schuman's research so special.
Yeah, I think there's three main things. The first is, of course, that she dared to ask a big open question. It's not more of the same, it's a big question. How does memory work? How do we remember? It's not a spiritual thing, it's something that is in the molecules. There's a mechanistic basis, and that was unknown. So big open question. Second thing, she realized as she is approaching the question over the last 3 decades, the technology available is not sufficient to answer the question. So she develops the technology. She has to cross the borders, and she comes up with something new. And then the third thing is that based on these new observations that you could only make because of the new technology, she would be able to change the hypothesis how memory works. You could even say it's a change of paradigm. You know, we're here in Hamburg, so the analogy to the harbors is obvious. You can either deliver the goods to the different places around the world by shipping them out, and there's a central factory, right, and then you have to ship it all. Or you ship the factory, and this is what Erin found. So you ship the factory to the place where you actually want to synthesize the proteins, and then you make the proteins there locally, and that was the change in paradigm.
Brilliant. So yesterday, we both and many others were present at the first Hamburg Science Summit, which is to celebrate, or to build bridges between science and politics and economics in Europe. And I was just wondering, what do you see are the strengths of programs like that in promoting Europe? Why is science in Europe? Why is it important that that is a focus?
I think it becomes even more important. It was always very important. One is, of course, to work together within the European research area, which is, of course, more than the European Union. I mean, the UK, Switzerland, even Israel. I think the European research area is very large, and these 3 countries are especially strong in science, so we want to have them in, and that is, an opportunity to be better than any one country could be on their own. The second thing is, of course, the role that Europe plays in the world, which is rapidly changing. I'll give you an example. The US, of course, we know there's the upcoming elections, but it doesn't matter for, the relationship to China, for example. It will not matter whether there's Harris or Trump. It will matter in many, many different ways. But Harris already said that she will stay on track with respect to the relationship to China. And we can already measure that the publications become less and less that are co-authored between American and Chinese scientists. So there's rivalry, but actually it hurts the science. And I think in that scenario, we can play an important role in Europe. Because first of all, we have this very long-term friendly relationship to the United States, and we should maintain those bridges. But second, we also want to continue and collaborate with China. We have to be aware of the risks. We have to do what we call the de-risking. We have to look carefully what we're doing and in which areas we cooperate. But it's important to do that. And for example, now we've invited the president of the Chinese Academy to join us in Berlin in only a couple of weeks from now to celebrate 50 years of our collaboration. And we want to continue, and we can actually do collaborations that are currently not possible between the United States and China. And since science is a global endeavor, I think Europe has this important role of building bridges in a multilateral world that is full of geopolitical conflicts.
So you touched on the geopolitical conflicts there, and as you alluded to, we do live in a world that is very uncertain. After some years of stability, there are wars where we didn't expect them, there are culture fractures which perhaps we didn't expect. Things feel a bit fragile. And I was just wondering, can you find some positivity, thinking about science in the European context, can you find some positivity that we can look forward and say, yes, it is all fragile, but we can find some reassurance in the way our science works?
Oh, absolutely. I mean, one thing to remember is that all scientists speak a global language. And I don't mean the English language, that is a prerequisite, but it's more the mindset. It's like rationality. It's about, observing things, about trying to be neutral, trying to get to the underlying truth of things and all of that, rationality, evidence-based decision-making. And that scientific language that unites us all is, incredibly important in the world that we see it, because we have these populists everywhere, we have them here. And these populists are actually fighting science because they don't want to have rationality. And so the positive thing that I want to say is that we are united with people around the world. They may be in very difficult situations, who share this thinking of enlightenment, basically the tradition of enlightenment. And I think what is also great about Europe is that legislation here allows us to maintain these bridges to those individuals who share that common language. And that can be even in Russia. So currently we're not allowed to spend money in Russia, and there's good reasons for it, as you know. But when individual scientists in the Max Planck Society or somewhere in Europe say, I maintain a contact to my colleague who's equally badly affected by politics, but who is a great person, who is very rational, and we speak the same language, then those bridges can be maintained. And that we have legislation here in Europe and constitutions that allow us to work in this way and that give us those freedom rights, I think it's really something to acknowledge.
Brilliant. It's a great thought to finish with. So now we get to the heart of the ceremony, because of course it is time for the presentation of the certificate. And I would like to invite Lothar Dittmar and of course Erin Schuman to the stage for the presentation. Okay.
Ja, wir kommen zum Finale und das ist die Urkundenübergabe. Wir verlesen noch einmal den Urkundentext auf Deutsch und auf Englisch. Ich beginne mit der deutschen Fassung. Die Körber-Stiftung vergibt auf Grundlage des Vorschlags des dazu berufenen Kuratoriums den Körber-Preis für die europäische Wissenschaft 2024 an Erin Schuman, Max-Planck-Institut für Hirnforschung Deutschland. Erin Schuman wird ausgezeichnet für ihre bahnbrechenden Arbeiten auf dem Gebiet der Neurobiologie. Ihre Forschung hat das Verständnis des Gehirns revolutioniert. Mithilfe innovativer Methoden entdeckte sie, dass und wie Proteine lokal an den Verbindungsstellen zwischen den Neuronen hergestellt werden. Dieser Mechanismus stellt die nötigen Proteine für die Kommunikation zwischen den Neuronen, die Speicherung von Erinnerungen und die Entwicklung des Gehirns insgesamt zur Verfügung. Ihre Erkenntnisse zur lokalen Proteinsynthese haben eines der Kernprobleme der Hirnforschung gelöst und eröffnen neue Wege zur Erforschung schwerer Hirnerkrankungen. Jetzt folgt Herr Kramer mit der englischen Version.
Okay, ready? In accordance with the proposal of the appointed Board of Trustees, the Körber-Stiftung awards the Körber European Science Prize 2024 to Erin Schuman, Max Planck Institute for Brain Research, Germany. Erin Schuman is awarded the Körber European Science Prize for her pioneering work in neurobiology. Her research has revolutionized our understanding of the brain. Using cutting-edge methods, she discovered that and how proteins are synthesized locally at the interfaces between neurons. This mechanism provides the protein needed for communication between neurons, memory storage, and overall brain development. Schuman's insights into local protein synthesis have solved one of the core problems of neuroscience, and they have opened up new avenues for research on serious brain diseases. Thank you very much, Erin. All the best. Congratulations.
Thank you. Thank you.
Sehr schön. Okay. Your applause.
To start the celebration that the prize has been awarded, I would like to invite back our musicians. And we will be hearing again from Maximilian Beer on the violin and Jonathan Grossman playing the cello. And they will be playing 2 pieces for viola and cello and Grotesque by Rebecca Clark. So please welcome our musicians. So we have reached the end of this morning's ceremony and another wonderful celebration of European science. I hope that the little protein factories in close to your synapses in your brain have been very busy creating good memories of this event. For those of you in the room, there is now a champagne reception next door to which you're all invited. For those of you online, I'm sorry there's no champagne for you, but perhaps you can get some of your own. And thank you so much much for joining us for this wonderful celebration of the Körber Prize 2024. Thank you.